Hi everyone. My name is Daniel Voskergian, a researcher from Al-Quds University from Palestine. And today I'm so honored to present you our research entitled Stage Disease Grouping, Scoring and Modeling for Predicting Diabetes Complications from Electronic Health Records. This work is executed with the collaboration of Prof. Malik Youssef from Zifat Academic College and Prof. Borjo Bakir from Abdullah Gol University. Much appreciation to both of them. In this presentation, we will go through a brief introduction, the motivation behind our study, the utilized data set, the proposed methodology, the experimental results, and finally, we will conclude with some final takeaways. As a brief introduction, diabetes mellitus is a chronic metabolic disorder characterized by its insufficient insulin production or impaired insulin utilization. Diabetes remains a critical global health concern, specifically in low and middle income countries, contributing to high rate of morbidity, disability, and mortality. In this aspect, increased glucose levels beyond the average level in the bloodstream may damage major organs over time, often leading to severe complications. These are broadly categorized into microvascular and macrovascular conditions. Notably, complications can account for over 68% of diabetes-related deaths. Early detection remain a challenge, since complications typically emerge in later stages. Therefore, medical checkup and routine screening for patients with diabetes. However, early prediction before doing such tests could alleviate the health burden of diabetes, improve care pathways, enable preventive measures, consequently delaying or slowing down their onset and development. Nowadays, we are witnessing a widespread adoption of electronic health records, which enable access to structured medical data such as diagnoses, lab tests, treatments, or clinical outcomes. When combined with machine learning, EHR provide like a valuable resource for analyzing disease progression, identifying risk factors, and enabling personalized interventions. However, as we know, real EHR access is typically limited or restricted by privacy and regulatory constraints. To address this issue, usually we use synthetic EHR generated by deep generative models, which offer a promising solution. Such datasets replicate real-world patterns with no one-to-one correspondence to actual patients, which tend to minimize the re-identification risk and preserve the data utility. In this study, we utilized synthetic clinical health records, tracking the diagnostic trajectories of diabetes patients, with the main aim to uncover associations among diabetes-related pathologies and to predict one of four main critical diabetes-related complications, including retinopathy, ischemic heart disease, chronic kidney disease, and amputations. To achieve this, we have utilized a novel feature engineering integrated with XGBoost feature selection. Actually, this part was implemented in CAMDA 2024 challenge. However, in a recent challenge, we have advanced our framework by incorporating the grouping, scoring, modeling strategy. Here we introduce a new concept that we will define later on called stage disease groups. Regarding the utilized dataset, actually we have used the one developed for CAMDA 2023 challenge based on a real cohort of nearly 1 million diabetes patients using dual adversal autoencoder derived from the health population database provided by the Andalusian health system in Spain. Regarding the structure of each SEHR record, it contains chronologically ordered visit sequences, where each visit, expect the first one which holds the gender value, the remaining ones hold an age range in the form of decade-based labels and a set of chronic diseases in the form of ICD-9 manual codes. The overall data set contains 83 ICD-9 codes with 10 age range labels and 2 gender values. Now let's move forward to our core methodology. As we can see here, this is a snapshot of our utilized data set. In order to prepare it for binary classification, actually we have performed several steps organized into 5 to 6 main components. Starting with the first component, the pre-processing phase. As we do regularly, we remove like empty records, we remove records with no gender value, with both gender values, with no registered visits. In addition, we have removed records without diabetes code. Here, we only retained patients with a diabetes diagnosis. Moreover, we iterated over each column to restructure the data. As we can see here, visits with no pathology codes were set to null. Visits or misordered visits were corrected by placing the age range label first. We have decomposed each visit into pairs, as we can see here. And finally, we have ordered them according to the diagnostic code for consistency. Then we iterated over each record and performed additional steps. For instance, here we have retained only the first occurrence of the chronic disease. We have removed null visits and re-indexed the remaining visits sequentially. We have filled the age range label, the missing one, with the next value, or the previous one if the gap was in the end. And we have removed the record which holds like no valid age range labels. We removed it completely. Moreover, we have removed the records which contain the diagnostic of the complication before the diagnostic of the diabetes. Finally, we have discarded all visits that appeared before the diabetes onset. These steps actually are important and crucial to have a data set that capture the disease progression for diabetes patients, which aim to make like more accurate prediction of diabetes related complications. Till now, as we can see here, such data set is considered a multi-label classification problem in order to simplify the modeling, like deeper insights or clearer insights. We have adopted the binary classification approach. As we can see here, like to create the such data sets, we selected instances which holds the required endpoint and like put it as a positive class. We removed the visits that appear after this endpoint to prevent the data leakage. The remaining has been held to negative classes. At this end, we have the resulting data sets are considered unbalanced data sets, which can lead to biased models. To mitigate this issue, we have performed random undersampling to keep like the same numbers of positive and negative classes. So in the feature extraction phase, we have extracted all distinct combinations and represented each SEHR with 2 plus T dimensional vector. Now, here to preserve the temporal order of visits, we actually encoded each feature with the visit index in which it appeared. Finally, after this phase, we have done some min-max normalization to scale all values. After this phase, we have performed the feature selection using XGBoost algorithm. Here we have retained the top 200 features and used it to train the model using our GSM approach. This is the whole framework of the grouping, scoring, and modeling approach. As we can see in the first component, the grouping one, we have organized the pathology codes into K-coherent groups according to the medical specialty or the body system affected. For example, metabolic disorder group, cardiovascular diseases group, and so on. Moreover, since each group or each feature in that group holds an age range label, we further divided such group according to their common age range onset into early, mid, and late stage in life. So the resulting groups are now more fine-grained groups that captures the variation onset. From now on, we will call them stage disease groups or groups in general. Afterward, the G component utilizes two inputs, the grouping that we already extracted from the previous phase with the bag of feature training dataset to create group-based sub-data sets. As we can see here, each sub-data set is a subset of the training data. However, it holds only the features that reside in each or in the corresponding group. In addition, as we can see here also, we have preserved the class label for each data set. These sub-data sets are then forwarded to the scoring component. The scoring component aims to analyze each group-based sub-data set to score and rank those groups accordingly, according to their classification or discrimination power in the classification task. For instance, we have performed a stratified Monte Carlo cross-validation approach with a machine learning algorithm such as random forest to compute a topic score or a group score. The group score comes in the form of the mean metric or mean performance metric, such as accuracy, performance, F1 score, or recall. We can choose any metric or any combination of them to score topics, to score how well the features in that group has a discriminative power in the classification task. So after ranking them, we move to our last component, the M component, which takes the ranked groups and try to find the top R ranked group that provide the best performance to train our final classifier. So let's move forward to the experimental results. Now to streamline the findings, I'm going to concentrate on the first endpoints, the retinopathy and the ischemic heart disease. Regarding the retinopathy, as we can see here, we can see the top 15 ranked groups that in somehow are dominated by the model for predicting the retinopathy endpoint. As we can see here, the cardiovascular disease, metabolic disorder, mental disorders appearing in later stage with the metabolic disease appearing in mid stage, we can see that they have an effect for such vision-related complication for diabetes. Now, to evaluate the effectiveness of the proposed approach, we have evaluated four main models, where we try to train those models on the accumulated top-ranked groups. Each point here represents an accumulated top-ranked groups. If we look specifically for the area under the curve, we can see that XGBoost performed the best with approximately 84% AUC. In addition, it performed the best with the F1 score, like 76%. Although Random Forest performed the best in accuracy, however, it tends to have a reduced sensitivity, as we can see in the F1 score figure. Similar performance trend can be found in the ischemic heart disease. However, here we can see that the dominating groups are mental disorders, which sometimes underemphasized in the prediction models, but they can be important for predicting the ischemic heart disease. So from this table, we can see here that we can see like shared groups. However, one significant difference may be their onset. For example, although we see some groups are shared between both endpoints, however, some groups like appear in early stage, some groups appear in like late stages. So maybe their onset can have a significant effect for the prediction of the type of the complication. Similarly, here we have tested our approach using 4 different algorithms. We can see here XGBoost performed the best in regard of the area under the curve and F1 score. I don't want to elongate so much, so I'm going to the conclusion section. Here we have developed a prediction models for diabetes complication using a novel feature engineering, feature selection, and the grouping scoring modeling strategy. One thing to note here is that we try to like make a shift from focusing on individual features to like clinically meaningful structured groups for using them as a prediction features with the aim to enhance the model interpretability. Although we got good results, however, external validation is needed for clinical implementation. Finally, thank you for having me, and thank you so much.
Thank you, Daniel. So any question? Is our questions on? No question? Is everything clear? You have one? Okay.
Yeah, I have a short question. Did I understand correctly from your presentation that you used the 2023 data for your analysis?
Yes, exactly.
Is there any particular reason for that? I mean, would the same approach also work with the
Well,
newer data?
yeah, well, we tried to access data at that time before submitting our abstract, but we couldn't access it. Therefore, we have used the one we have used in 2023 and 2024 challenge. But our intention is to use it for the newer data if we had the accessibility for it. Thank you for
So there were
your question.
technical problems, or what was the issue?
Again?
Were the technical problems with the
It
download,
seems
or what was the
technical
issue?
problems. I don't know because we have contacted through email, but I didn't get a response. So in order to like keep up with the deadline, so we have used the first one. But as I told you, our intention now is to test our framework, our proposed approach for the 3 data sets that we have till now. The one specifically developed for this recent challenge.
That will be
Thank
interesting.
you for your
Thank you.
notice.
Okay, write us an email because we didn't receive anything. Probably there was a problem at some point. So you can write us an email and we can feel that. So if there are no more questions, so we have now the coffee break.